All right. Good morning, everyone. Wow, it's the exact same amount of people as last time. Sorry, the exact same amount of people in the 8:30 section as the 9:30 section today. All right. Okay. So, as you have likely seen from the announcements already, we got quite a lot going on the next 2 weeks. So it's gonna be fun. So we got 3 quizzes in the next 2 weeks, as well as the exam. So here for that. So quiz 4 is today. Opens up now, and you have until tomorrow morning at 9 a.m. to take it. Covers lessons 11 and 12. Quiz 5 is going to be on 9 a.m. on Friday, and then closes on Saturday morning. Covers lessons 13 and 14. Quiz 6, the quiz window will open up on Wednesday the 7th, October 7th. So not this Wednesday, but the Wednesday after that. And then exam 2, the window opens up on Saturday the 10th and it closes on Tuesday, October 13th. That covers lessons 11 through 18. Okay? So that's all I had to say on that. So any questions on that? Any quick homework questions you want to look at? All right. Then, without further ado, ladies and gentlemen, let's talk about some implicit differentiation. So, let's go over some brief definitions real quick. So a function in explicit form is something we've already seen before quite a bit in this class. So I'll just briefly give you an example of what that is. So we have y equals x cubed plus 3 cosine of e to the x, quantity to the 5th. So basically, it's just some random function that has y by itself, and then x does whatever it does here. So basically, we have some function of x, and then y completely on its own. So what I mean by that is no powers, no radicals, no logarithms, no nothing like that. Just y is by itself, and that's it. So no powers, radicals, logs, etc. Okay? On the other hand, meanwhile, a function in implicit form is a little bit different. So we have something like this for a function in implicit form. So we have x squared plus y squared equals 9, or something like x times y equals sine of y. So the idea is that in implicit form, we can't really solve for y here, or at the very least, it's not really beneficial to. So in this case, we have, so can't always isolate y. So here's the caveat with this. So in a function in explicit form, well, we already know how to differentiate that. You can we're going to have to use chain rule, we got to use power rule, we got to use all these derivative rules that we've already established. But with a function in implicit form, we have to be careful in differentiating this. So how to find dy over dx here? Okay? Right. So in a situation like this, that's where the implicit differentiation rule is going to come into play. So hence the title of our lesson today. Okay? So we're going to have to use the aptly named implicit differentiation. Okay? So we'll get into that in a bit, but for now, let's go ahead and give us some background to see where we're going with this. So the thing is, we already know how to differentiate explicit functions like I already established. So if we were to do that, let's say, all right, well, let's focus on this. So let's take the derivative of x squared plus 3x minus 7 raised to the power of fourth. So if we were to differentiate that, well, what's up?
Oh, no, go ahead.
Okay. If we were to differentiate that with respect to x, then what would our derivative be? So I'll give you guys a second to take a look at that. Go ahead.
I got 4 times the quantity of x squared plus 3x minus 7 to the third power times 2x plus 3.
Times 2x plus 3. Okay. So what happens here is that, like we said, this is just a combination of applying the chain rule as well as the power rule. So the reason I'm doing this is to say, all right, well, let's suppose we let y equal the quadratic. So we have this quadratic here. Let's just simply denote that by y. Okay? So then as a result, well, as we already sort of saw here already, then the derivative of y with respect to x is just 2x plus 3. So dy over dx goes here. Okay? So if we were to rewrite this expression here using these notations, then what we end up with is 4y cubed times dy over dx. Okay? And so the reason I'm doing this is because if we were to rewrite this part of the equation here using said notation, then what we get is that we have the derivative with respect to x of y to the fourth. Okay? So what that says is that let's focus on this part here. So what we say is that, all right, if we have y as some function of x, then what that appears to say is that if we take the derivative of some function of y, then chain rule says we take the derivative like we normally do with the y part, but then because of chain rule, we have to multiply dy dx into there. So here's what that says. So same general idea still holds. Even if y isn't explicitly in terms of x. In terms of x. Okay. So to generalize this to just any function in general, here's what this says. So in general, chain rule gives the following. So the derivative with respect to x of some function f of y. So again, we're letting y be some function of x here. Then what that says is that the derivative of f of y is just f prime of y times dy over dx. Okay? Is what this says. So I'll box this in here. All right. We'll box that in, and then for this part, what this says is that we differentiate f of y as you sort of normally would. then multiply dy over dx because of chain rule. Okay. So what happens in this case is that all we're doing is we're letting f of y equal y to the fourth. So that would just be a quick application of power rule for this part here. This is what's happening there. Okay? So then what I'm going to do is I'm going to denote this by asterisk. And you'll see why in a minute. So that way I can just refer to this equation here as star. So as a result, this gives us the following idea to find the dy dx with implicit differentiation. So to find dy over dx with implicit differentiation, what we have to do is treat y as a function of x, and then differentiate equation with respect to x using derivative rules and asterisk. Okay. So basically, that's the basic idea behind utilizing implicit differentiation and star here. So basically, we treat y as a function of x, and then we use all our derivative rules as well as this to be able to not only differentiate this, but then we have to use algebra to from that to get dy dx by itself. Okay. So any questions on that procedure before we move on to our first example? So let's move on to our first example then. So example 1 asks us to find dy dx for the following curve. So we have x squared minus y squared equals 4x plus 7y minus 3. And we have to use this to find the equation of the tangent line at 3, -7. Okay? So the thing is that if you're given a point like this, you can assume it's already a point on this curve. So you can check this on your own by saying, okay, let x equal 3, y equal -7, plug them all into here, and then just check to make sure that everything checks out the way it should. But for now, I'll just say, I'll leave this as an exercise for you to check this. Okay? So what I'm going to do is we're going to say, all right, so let's go ahead and say, all right, well, first figure out what's going on with this dy dx thing. So to find dy dx, so first find dy over dx. All right? So finding dy dx is going to follow a two-step procedure here. So I'm going to denote them by step A and step B, respectively, because I don't want to confuse them with the three-step procedure that we're going to use to find the equation of the tangent line. Okay? So with step A, the idea is that, like I said in the idea above, so differentiate all terms on both sides with respect to x. Okay? So utilizing that idea, we say, all right, well, we have d over dx of x squared minus y squared equals d over dx of 4x plus 7y minus 3. Okay? So I'm going to do the right-hand side for you guys, and then I'm going to ask you guys to do the right-hand side for me. So the left-hand side, all we have to do is focus on the derivatives of x squared and y squared. So the good news is that the derivative of x squared with respect to x, well, we already know how to handle that, because here we just have an actual explicit function of x given to us already. So in this case, you just have that power rule is just going to give you 2x. So that's it. No other like multiply by anything, no chain rule. It's just here's the power rule and that's it. But with y squared, that's where our asterisk rule is going to come into play. This guy right here. So here we say, all right, we just differentiate this like we normally would. So in this case, this would be 2y because power rule. But then because of chain rule, like as in y is a function of x, we have to multiply dy dx into this. Okay? So that's how that forms. Okay? Okay, so that's the left-hand side. So using this reasoning, what would the right-hand side be?
Would it be 4 plus 7 dy dx?
Exactly. So we have 4, because derivative of 4x is just 4. And then plus 7y, so that's just going to give you 7 dy over dx. And then this minus 3 is constant, so we don't care about that. Okay? So that's all said and done. So now step B, so now that we've differentiated everything, now we solve for dy over dx. Okay? So in this case, we say, all right, well, 2x minus 2y, dy dx equals 4 plus 7 dy dx. Okay, so the thing is that here, all we have to do is just sort of treat dy dx as its own quantity slash variable and then solve for it as we sort of normally do. So in this case, what we can do is say, all right, what we have to do is we have to get all terms with dy dx on one side and then all the remaining terms on the other in a situation like this. So in this case, let's go ahead and say add 2y times dy dx and then subtract 4 on both sides so that we can get everything with dy dx in it on one side and then everything else on the other. Okay? So as a result, this should net you 2x minus 4 equals 4, 2x minus 4, and then plus 2y dy dx plus 7 dy dx. Okay? But then what you notice is that, wait a minute, these two terms on the right-hand side have dy dx in them, right? So we can just factor out dy dx out of this. So we have dy dx of, or times 2y plus 7. Okay? So then as a result, this should pretty quickly tell you that dy over dx is then equal to what? Go ahead.
2x minus 4 over negative 7 minus 2y, or 7 minus 2y.
So here we have 2x minus 4 and then times 2y plus 7 over here.
Oh,
so
just divide the 2y plus 7 like that.
Yep, so just divide 2y plus 7. Okay? So this is dy dx. So the reason why we care about this in terms of working with, in terms of calculus is because as we've established with derivatives, this will give you the slope of the tangent line at any point. But here we have to do a slightly different procedure because we have an implicit curve here. So gives slope of tangent line at any point x comma y. Okay? So that gives us dy dx. So now let's use this to see how we can get the equation of the tangent line we need here. So now let's find the equation of tangent line. Okay. So now here's where our three-step procedure of step 1, 2, 3 is going to come. So step 1, slope of tangent line. So the good news is that, as we already established above, this quantity here represents the slope of the tangent line at any point. So here we already have essentially we already have our derivative. Now all we got to do is plug in our points to get the corresponding slope. So slope, or I shouldn't say slope. When I would say derivative, dy over dx, given above. So now let's, in this case, we have to let x equal 3 and y equal -7 to get our corresponding points. So let x equal 3, y equal -7 to get slope. Okay. So here we have, all right, well, dy dx equals 2 times, well, 3 minus 4 over 2 times -7 plus 7. Okay? So if that's the case, then that should tell you that our slope is then what quantity?
-2/7.
Yep, -2/7. Good. And this will give you your slope that we need here, as which I'll denote by m. Okay? So now step 2. So the good news is that with step 2, which is the point on the tangent line, with problems like this, they usually kind of give it to you already. So in this case, it would just be 3 common -7, as we stated in the problem statement. So given 3 common -7. So step 2 is usually pretty nice and quick in a problem like this. Step 3, well, now we just have to find the equation of the tangent line. Okay, so we got our point on the tangent line as well as its slope. So now we just plug this into our good old point slope form to get the desired result. So if you recall, it says that we have y minus the y coordinate, so -7, equals the slope, so -2/7, times x minus the x coordinate, so 3. All right? So then what this tells us is that, well, we have y plus 7 equals, distribute -2/7 to both terms. So you get -2/7 x plus 6/7. Okay? So then if we were to subtract 7 over to the other side to thus isolate y, what would our final result be? What would our slope of the tangent line equal? Go ahead.
Would be y equals -2 sinus x minus 43/7.
Yep, 43/7. Good. Because all you're really doing is once you subtract 7 over to the other side, you essentially just have -6. You would have 6/7 minus 7. So then using common denominators would get you this as your final answer. Okay? So, any questions on any of that?
In the first step?
Step 1 or step A?
No, like
So step A?
Yeah, step A, the one where you find dy over dx. How did you get, in the last step from 2x minus 4 equals dy over dx times 2y plus 7? How did you get 2x minus 4 over 2y plus 7?
I just divided 2y plus 7 over to the other side here. So we have 2x minus 4. So then because remember, this expression here is equal to this, right?
Mm-hmm.
So then you just divide 2y plus 7 over to the other side.
Oh,
Okay. Any other questions on any of that? Okay. All right. Example 2 then. So example 2, we have to find the slope of the tangent line to the curve below for the points 1, 0. So here, essentially all we're really doing is just sort of the step 1 from the last example. So we're still doing step A and B, but all we really have to do here is just find the slope of the tangent line. So essentially just find dy over dx at 1, 0, or x equals 1, y equals 0. Okay? Okay, so, like we said, so step A, differentiate both sides with respect to x. Okay. So we have d over dx of, let's see, so we have 6x cubed plus 5x cubed y cubed minus 3 times sine of y equals d over dx of 6. Okay. So with this, I'll spare you the details of the right-hand side because, well, it's just a constant, so derivative is 0, no questions asked. So now let's go ahead and differentiate the left-hand side. So if we were to differentiate the left-hand side, we have 6x cubed. We have to differentiate 6x cubed. We have to differentiate 5x cubed y cubed. So 5x cubed y cubed. And then we have to differentiate 3 times sine of y. That's 3 times sine of y. Okay. So let's start with the easy ones. So let's start with the first term, 6x cubed and 3 times sine of y. So what would the derivative of 6x cubed be? 18x squared. That's just power rule, no questions asked. What about 3 times sine of y? Remember, here we just have y here by itself, right? So in this case, we have to harken back to our asterisk rule, right? So what does our asterisk rule say here? So if you remember, we have to differentiate f of y as you normally would, but then because of chain rule, you have to multiply dy dx into that, right? So in this case, we have to differentiate this like we normally would, but then we eventually have to multiply dy dx into this, right? So what would the derivative of this be then?
So what do you like use chain rule first and then implement not dy over dx and wherever y is?
Yeah. So in this case, so if we apply our asterisk rule, then what would our derivative of 3 sine y be?
Would it be negative 3 cosine of y times dy dx?
Why is there negative?
Oh wait, no.
Yeah, so we won't incorporate the negative just yet, but yeah, that's the idea. So 3 times cosine of y times dy over dx. So that's the derivative there. Now here's where things get a little bit more interesting. So we have, on the second term, we have 5x cubed, which is one function of x, times y cubed, which is another function of x. So it seems that we have a product of two functions of x. So if we wanted to differentiate a product of two functions, what rule would let us do that?
Product rule.
That's a good, I like that answer. It's a good answer. So if we were to do that, we say, all right, well, what would the derivative of 5x cubed be? Well, do the same thing we just did above to get 15x squared. But then what about the derivative with respect to x of y cubed? Yeah, 3y squared times. So differentiate like you normally would, then
You add dy over d.
yep, well, times dy dx. Okay? All right. So then as a result, then product rule will then tell you that the derivative is, well, first times derivative of the second. So we have 15 x cubed y squared times dy dx. Sorry, not equals, plus second times the derivative of the first times second. So we have 15x squared y cubed. Okay. So that would be our derivative of all three terms with respect to x. Okay. So as a result of that, we have 18x squared from the first term plus 15x cubed y squared times dy dx plus 15x squared y cubed, and then minus, because of the minus here, minus 3 times cosine of y times dy over dx. So that this all is the left-hand side. And then because of the right-hand side here, this is just a big fat 0. Okay? So after this, we say, all right, well, now we've differentiated everything. So now step B is solve for dy over dx. Okay? So one remark I'm going to make on something like this is that you could just, do what we did in the last example and just, go through all the algebra, solve for dy dx, and then you're done. But one thing that might make your lives a bit easier in a problem like this is to say, all right, well, if I just need the slope at a particular point, sometimes it may be more optimal to plug in the point first, then solve for dy dx. So notes, if you just need dy over dx at a point, it can be more optimal to plug in points right after step A. Okay? So what that means is that we say, all right, well, we already know that if our point is 1, 0, then that means that we have to let x equal 1 and y equal 0. So if we take our equation from step A and plug in our points, then we have, 18 times 1 squared, so just 18, plus, we have y equals 0, so because of the 0 factor here and here, we just have 0 times dy dx plus 0 for these middle two terms. And then minus, 3 times cosine of 0, but, what's cosine of 0? Just 1. So we have 3 times dy over dx equals 0. So then what you notice is that our life becomes a lot easier now, doesn't it? Because now we just have 18 minus 3 times dy dx equals 0. And then that should pretty quickly tell you that dy over dx is then just equal to 6. And that's example 2. So, any questions on that? Okay. So now let's move on to our last example. So, I'm going to give you guys a second to write that down. Okay. So, example 3. Find dy dx for this curve 4 times tangent of x divided by y equals 11x. Okay? So in this case, all we really have to do is just do our usual 2-step procedure here. So step A, differentiate both sides. So we have d over dx of 4 times tangent of x divided by y equals d over dx of 11x. Okay? So, I'm sure you can pretty quickly guess at this point that if we take the derivative of 11x with respect to x, well, that's just 11. I'll let you check the details of that on your own. But, let's focus more on the left-hand side now. So, if we were to differentiate 4 times tangent of x divided by y with respect to x, well, what do we notice? So we have 4 times tangent of x divided by y. So what we have here is that since y is a function of x, that means so is x divided by y. So ultimately what this tells us is that we have one function of x inside of another. So let me go ahead and write that down. So one function of x inside another. So, as a result of this, we're going to need to use what rule? What derivative rule? Chain rule. Good. Okay, good. So, as a result of that, well, let's go ahead and let g of x be the inner function, and then f of x be the outer function. So, if we were to identify our inner and outer functions in this situation, what would they be here?
Would the inner be tangent x divided by y?
Not quite.
Or is this x divided by y?
Yeah, you just want x divided by y. Because x divided by y is inside tangent, which is itself a function. So then that would tell you that the outer function is then tangent of x. Okay? So let's focus on f of x for a second. So if we differentiate that, well, that means it's going to be 4 times the derivative of tangent, which is secant squared. Good. Of x. So that means ultimately f prime of g of x, well, you just replace x here with whatever g of x is. So in this case, x divided by y. So you have 4 times secant squared of x divided by y. So that would be f prime of g of x. But now, what is g prime of x going to be? Because that's the last thing we need for a chain rule from this part. So, if we were to differentiate g prime of x, if g is x divided by y, well, how do we handle this? What rule are we going to need?
So we're going to use the quotient rule.
Okay, good start.
It's going to turn out to be y minus x dy dx.
Right.
Because low d high, you get y multiplied by 1 minus high d low, which would be x multiplied by the derivative of y, which is dy dx, over low low, which would be y squared.
Right. So for those of you watching at home, let's go ahead and recap what he said. So in this case, you have x divided by y, so quotient rule. So in this case, if you call quotient rule, this is low d high, so y times the derivative of x with respect to x, so that's just 1. And then minus x, so that's the high, minus high d low, so that's x times the derivative of y with respect to x, so just dy dx. And then all over the lower function squared, so just y squared. Okay? So for those of you watching at home, that's the derivative of g in that case. So now that we have that, that says, all right, well, the derivative of 4 times tangent of x divided by y is just, well, multiply these two guys right here to get 4 times secant squared of x divided by y times y minus x, if I can write x correctly, that is. So we have y times, so y minus x times dy dx all over y squared. Okay? And then that's just going to equal, and because of our equality up here, we have this is just equal to 11. Okay? So this is now step A. So now step B, now we just have to take this whole thing and solve for dy dx. Okay, let's do that. So we have 4 times secant squared of x divided by y. So I'm going to rewrite this a tiny bit differently. I'm going to rewrite this as 4 secant squared divided by y squared times times y minus x times dy dx equals 11. So now our goal from this is to go ahead and take all this and solve for dy dx embedded in here. So if we wish to do that, what would be a good place to start? Any thoughts, comments, suggestions? Go ahead.
So you can put you subtract 11 from that side, and then
I mean, that's not something. It's not that you can't do that. It's just more how would that help, I guess. So we have that this expression here, which involves dy dx, is multiplied by this whole thing, right? So what could be one thing we could do with this?
you want to multiply by the inverse.
Exactly. So if we were to divide 4 times secant squared and then multiply y squared over to the other side, we'd have y minus x times dy dx equals 11, so times y squared, and divided by 4 secant squared of x divided by y. Okay. Okay, so that's a step closer to what we need. So what will be the next step from this? What would be a good next step 2?
Would you then divide by y minus x to get dy dx by itself?
Well,
Oh,
not quite, because remember, you have x times dy dx as one term here. So
so you would add y and then divide by negative x?
add y? This is positive already.
Oh, subtract y.
There we go, subtract y. So we have negative x times dy dx equals 11y squared over 4 times secant squared of x divided by y, and then minus y. So then what that tells us is that, all right, well, as you said, the next appropriate step would be to divide by x. But before we do that, what I'm going to do right quick is I'm actually going to simplify this a little bit. So what we notice here is that we have this fraction here minus y by itself. So what we could do to make things a bit simplified in some sense is let's apply common denominators. Okay? So what we can do is say, all right, well, on the second term, if we were to multiply and divide by 4 times secant squared, we have 11y squared over 4 secant squared, x divided by y, and then minus y times 4 secant squared of x divided by y over 4 secant squared of x divided by y. So then as a result, because now we have common denominators, we can say that this is the same thing as 11y squared minus 4y times secant squared of x divided by y. All this divided by 4 secant squared of x divided by y. Okay? Okay, and then now we can divide by negative x to get the dy dx by itself. So dy dx is then 11y squared minus 4y times secant squared of x divided by y. All that divided by negative 4x times secant squared of x divided by y. Okay? So the nice thing is that this is the final answer, and this is not wrong. One thing I will note, however, is that if you're in a situation where you have a multiple choice on a homework, a quiz, or exam, and you see something like this, or you have something like this as your answer, but you don't see that as one of your choices, one thing that could help in this situation is multiply and divide by negative 1 to see if you can get the answer from that. So multiply / divide by negative 1 to see if that can give you your answer. So if you do that, you say, all right, if I have a negative 1 on top and bottom and distribute, then on the bottom I would just have 4x times secant squared of x divided by 1. And then if I distribute negative 1 on to these two terms here, this can be rewritten as 4y secant squared of x divided by y minus 11y squared. So this gives you two ways to express your answer here if you are in the situation where one of the options is not given to you. So you can then multiply and divide by negative 1 to see if that fixes it. Okay? And the reason I'm doing this is to say, all right, so do this if your answer is not a choice on a homework / quiz / exam. Okay? Okay? So, just a quick remark on that before you guys take off and see that on the homework and like, wait, I did everything right, what happened? So, yeah. So that's all I have for today. So do you guys have any questions on all of that? Yeah? Or, oh, sorry, I thought you had that. Sorry. Does anyone have any other questions? All right, well, you guys get out a minute early. So, enjoy your 1 minute, extra minute of freedom, and I'll see you guys either in Zoom office hours tonight or either on Wednesday when we will start talking about related rates.